Yeah, so go ahead.
Thank you, Jesus. Hello, everyone. So, as the conference was postponed because of obvious reasons, but I'm very happy to join. And as Paul said, that conference is going very smooth, and I also enjoy it quite much. However, a lot changed in this project over the time, especially that I'm currently in Poland, moved to Poland. However, all the work was experimentally done at National University, Australian National University. So I added a little bit subtitle, which will be explained later in the talk. So if TAN contact and Bogoliubov excitations, obviously we have to talk about polaritons. So not going into details because most of the people here are quite very familiar with the concept. We are here in this talk focused on polariton nonlinearity in the quantum level, meaning how polaritons do interact and how does it affect the Bose-Einstein condensate made of them. If Bogoliubov excitations, if interactions, so then the dispersion of collective excitation is modified, and there were quite a few attempts to measure it. So here is just an overview of several of them. So one can use a parametric palm probe when the scattering to both excitation branches is forced in the palm probe scheme. Both excitation branches were kind of seen in a very strong and pulse excitation in the center column, and obviously there is this very famous demonstration of Bogoliubov excitations in photoluminescence in 2008, however with no signatures of Gauss branch. And very recently another attempt with new techniques last year were performed, where under resonant excitation with filtered out laser one could track what is happening with excitations when we filter out the very strong laser, or another very clever way was to extract the dispersion from G1 treatment. But now let's just briefly go through Bogoliubov excitation. What does it mean, right? So this means that when one uses Bogoliubov transformation, the interacting Hamiltonian of a BEC can be diagonalized with a new spectrum of excitations, which is very characteristic in low wave vectors. It's linear, explaining the superfluid properties of a BEC. However, at high momenta, it recovers the single particle dispersion shifted by a chemical potential. And what about occupation of these branches? When one takes this theory into account and calculate the occupation, one can see that the branches can be populated by thermal depletion, so real excitations of the condensate, and quantum depletion, which is independently present and occupies excitation branches independent of temperature. In our approach, we use high quality gallium arsenide microcavity from Princeton University, where we can create a large enough and high density condensate optically trapped with a ring excitation as depicted on the right here. When one can see at the highest densities, we create a single mode condensate, which is flat in density distribution, which indicates that this is the Thomas Fermi regime, which is interaction dominated. And this is the region where we can probe these multi-particle effects of the condensate. So how to measure Bogoliubov branches? Obviously not so straightforward, because the emission from the condensate will dominate completely the spectrum, and it will saturate the CCD camera. So what we have developed, we used an edge filter in momentum space to simply cover the strongest emission to uncover the very weak signal from both excitation branches, and then allowing us to analyze what is happening with them and what is the occupation of both branches. We have found that at negative detuning, the ghost branch, which should be populated by quantum depletion, shows some weird occupation dependencies, which are far from predicted k⁻⁴ dependency predicted from the equilibrium theories, and we observed that for positively detuned condensates where Hopfield coefficient of excitons was more than 50%. So that was the motivation of work which I will present now. So as we see that positively detuned polaritons behave like equilibrium BECs, so improved, so we realized that this phenomenon of quantum depletion, meaning that quantum fluctuations mediated occupation of branches, or having this particular k to the -4 dependency, allows us to extract a parameter called a tan contact, which is very relevant in quantum gases, especially in unitary regime. Why is it relevant? Because the author of the work, Sheena Tan, indicated that many thermodynamic properties of a quantum gas can be expressed with this parameter, which is, and the tan contact is basically a parameter measuring the probability of two particles being very close to each other in contact diameter, and they can scatter to excited states. So what we have done, we improved our experiment to detect far in the K space, and we reached beyond the inflection point and reached a twice higher density because of improvement of the laser. And we attempted to extract the tan contact. However, as you can see, reaching above the inflection point, which is here around 2, you can see that at high densities, Gauss branch gets populated above the k to the -4, indicating some parametric scattering and more interesting physics. So to attempt that, and to explain this, I will briefly introduce how to understand photoluminescence of excitation branches, right? So looking at the Bogoliubov transformation, annihilation of one polariton can be obtained from the microcavity in 2 ways, at least. Firstly, just an annihilation of a real excitation, which is observed routinely in experiments. However, the second part of the Bogoliubov transformation shows that annihilation of a polariton is with simultaneous creation of a real excitation. So the appearance of the Gauss branch is simultaneously with a creation of another excitation in the normal branch. However, because both branches are occupied, one can also expect stimulate the bosonic scattering to these macroscopically occupied states, highly excited at high energies. And now to understand what is happening in multi-layer cavity, which we are investigating, which has 12 quantum wells, we can start from an exact Hamiltonian, which Olivier will definitely talk in more detail tomorrow, where coupling of light with multi-layers creates also not only lower and upper polaritons, but n to the n-1 combinations of excitons which are orthogonal to the light, which means these are not dark excitons, but dark combinations of excitons which cannot be neglected in scattering between polaritons. So if one wants to create a Bogoliubov Hamiltonian out of it, we have to take into account all the scatterings between them. So here it's written in a compact form in the basis of the exciton operators. But when we want to now express this in polariton operators and all the possible scattering channels, it's quite messy, but let's go to the effective Hamiltonian, which was developed by Olivier and our friends from Monash University. Here we have a more or less typical interaction term for polaritons, which is scaled by Hopfield coefficients, plus uncondensed part, which is here written in a H3 approximation, so it's a mean value of the operators, but this allows us to include this dark states and uncondensed part in the Bogoliubov Hamiltonian. And now the result of it is as follows, that the new Bogoliubov excitation spectrum is dependent not only by Hopfield coefficients, but also on the non-condensed or reservoir density of the condensate of the whole system. And how does it look like in the spectra? It doesn't modify much the superfluid part, but it modifies a lot high K value of the excitation spectrum. Why? Because here the Hopfield coefficients of excitons dominate, so the interactions are much stronger. So we probe the excitation spectrum, but how to now distinguish how this newly developed theory is different from just putting polariton dispersion into standard Bogoliubov theory. So here it's quite, especially that we are limited with our wave vector range, and we cannot, unfortunately, probe the superfluid part of the spectrum. So we decided to measure the quasi-particle energy shift, so to compare how the dispersion is shifted with respect to the single particle dispersion, so the lower polariton dispersion below the condensation threshold. So if if the standard theory is the real theory, obviously, as the standard Bogoliubov indicates, at high wave vectors, the shift is approaching the chemical potential and single particle dispersion. But in the theory, taking into account Hopfield coefficients and uncondensed part, one can see a dramatic change in the behavior, especially that it's not reaching in this wave vector region a steady constant, right? So, and from the experiment, one can see that this is indeed the case. We show that at high wave vectors, the excitation branches must be fitted with the theory, taking into account these two things. So if we now can fit the dispersion both with the mu c, so the mu c meaning the chemical potential of the polaritons and the inclusion of reservoir, we can extract the blue shift from going from only from the polaritons and the total blue shift, which is easily measured from the experiment, and we can calculate what is the condensed fraction of polaritons, and one can see it's quite weird. It saturates about 50% at high densities, even though polaritons are not strongly interacting system, right? It's not like superfluid helium, but this can be explained by this kind of process that at very high densities we have this locking of bottleneck polaritons and pairwise scattering to the condensate, which simultaneously create another reservoir particle in the trap. This is why this value of 50% appears at high densities. And I would like to finish now showing the property, having measured both excitation branches in the whole K-space, one can extract now what are the values of the Bogoliubov amplitudes, which are here expressed by these parameters, which are just shown a few slides ago. And now, considering what is the mechanism of occupation of the branches, the normal branch are the real excitations, right, which are given by the distribution of occupations weighted by the first Bogoliubov amplitude, and the ghost branch is the same, but with including quantum depletion. And knowing that, okay, yes, I'm finishing. Thank you very much for the info. So at high K vectors, the real Bogoliubov amplitude tends to 1, so we can approximate that measuring the normal branch, we indeed measure the distribution function of a real distribution function of polaritons, and this is far from equilibrium. Even though that our theory is equilibrium, we can see that experiment is not very much in the equilibrium. As you can see, it's nothing close to Bose-Einstein distribution, especially with high occupation of bottleneck polaritons. But now, taking this approximation, we can see that measuring both branches, we can extract directly amplitude Vk of the Bogoliubov spectrum of the Bogoliubov transformation, and this is what we have done here. You can see that, and I here highlight that the dashed lines are not fits to the data. These dashed lines are calculated based on the fits to the spectrum, and now we compare them to the real data, and we have quite good matching especially at higher densities, indicating that this inclusion of reservoir is indeed present in the experiment. So to summarize, we measured the full Bogoliubov spectrum and the improved measurement, and shown that few things must be taken into account to understand the shape of the spectrum, and we were able to directly extract the amplitudes of Bogoliubov transformation. The title is about TAN contact. We were inspired by TAN contact to measure all of these, but this theory shows that because polaritons are complex creatures, contact is mediated by excitons. So, to measure the real contact, we have to go to the regime in K vectors, probing the Bohr radius of excitons, unfortunately. So it's very far. However, investigating this project gave us a lot of insight on what is truly happening in the Bose-condensed regime of polaritons. Thank you very much.
Thank you, Maciej. I see that Nina has already raised her hand. Go ahead.
Yeah, thank you very much for this very interesting talk. I have a question. As we know, Bogoliubov approximation and transformation, everything is valid for the case when the fraction of non-condensed particles is much smaller than full density or full number of particles. But then in the end, you say that you measure the condensed fraction and it is above a little bit above 50%. So then how is it consistent?
Yes. So So you are absolutely right. But here the issue is that from this approach, naturally scattering between polaritons is mediated not only by the bright configuration, right? So the configuration giving polaritons and lower and upper polaritons, but also through these dark states which are always present here, and they naturally pop out here in this Bogoliubov Hamiltonian. And maybe saying I will use this in this way. One thing is that polaritons are not in thermal equilibrium, right? So this uncondensed part is not excited from the condensate, right? It's not excited from the condensate. Most of this uncondensed part comes from the pump, and obviously also from this parametric scattering. So this is why the condensate of polaritons is really can be treated with Bogoliubov approximation, but it's simultaneously in this soup of excitons being pumped from the laser. Plus all this complex scattering terms and so on.
Thank you.
Alexei, can you ask your question?
Yes, so there were predictions that the polarization should also matter. So if you have a linearly polarized condensate, then the dispersion branches of co-polarized and cross-polarized excitations should be split. So any evidence of that?
Yes. It's a very good question. We indeed measure this small splitting. And this is a basis of another project which we are soon finishing. But here, for the sake of this analysis, we haven't used polarization detection. However, to take this into account here, because these values are measured from both branches at the same time, because I do not use do not resolve both polarizations. Therefore, to include additional, one can include here additional degeneracy, which is included in this data, that the measured ghost branch and measured normal branch has to be divided on 2, because there are 2 normal branches and 2 ghost branches, co and cross polarized to the condensate, right, as you indicated. And yes, detailed studies should be also done. What is exact population of both branches here? Here we measure the average of 2.
Okay, thank you. Maciej, can I ask you, how does the effect scale up with the number of quantum wells in your microcavity?
What scales up with number of quantum wells? Could you repeat?
So you showed that in Olivier's theory, it depends on the number of quantum wells, basically. So can you tell us how?
So yes, so basically, obviously, Olivier definitely will say more details about this. But first of all, the nonlinearity scales quite naturally, which more or less everyone is used to. That as you have more and more quantum wells here, right? The G, the nonlinearity here, is for one quantum well. But if you have 10 quantum wells, your effective nonlinearity will be 10 times smaller, right? So this is why when measuring nonlinearity in polaritons, one has to always remember how many quantum wells are here. But what is essential for this this description is that without many quantum wells, if we have only one quantum well, only this exciton always couples to light. So this is the bright exciton coupling to light forming polaritons. But if you have many quantum wells, only one configuration of them is coupled in phase configuration, as it is sketched here on this scheme. But the interaction between polaritons, scattering between them, can be mediated between these intermediate states, which are out of phase, and there are n-1 configurations, orthogonal configurations of these excitons in quantum wells. So the nonlinearity, as we understand, possibly is not the value is not. I mean, how the nonlinearity is expressed will be shown tomorrow. But scattering between them must be taken into account through these dark states.
Okay, so Olivier, one last question or one last comment?
Yeah, it's maybe just a comment to say that formally in this Bogoliubov approach that we derived, it was in order to really to describe the experiment. And in this Hamiltonian that Maciej is showing here, really our goal was to fit the blue shift. So at the end, in the Bogoliubov, what we want to explain is the Bogoliubov spectra. And in this spectra, there are two kinds of energy shift. There is the energy shift which is given by the interaction, the self-interaction of the polariton within the condensate. And there is also the effect of the reservoir. And it turns out that in a multilinear system, this reservoir appears naturally because of these dark states. But really, here, the total blue shift is composed of the condensate blue shift plus the effect of the reservoir, which is something that, okay, people are used to in the community, I think.
Thanks,
okay.
And
okay, so I think